Hello, my name is Michael Gira, and together with my co-authors Ruisu Zhang and Kangwook from the University of Wisconsin-Madison, we investigated how to debias pre-trained language models via efficient fine-tuning. This is an outline of the talk today. First, I'm going to start with our motivation. Now, a fair word of warning, the next slide contains offensive material. The core of our motivation comes from the fact that machine learning models learn patterns from its training data. This can be useful because, for example, we can have a language model learn English grammar and syntax. However, there can be harmful and nuanced prejudice within this training data. For example, recent work examined the word-to-vec algorithm, which takes an English word and then maps it to a semantically meaningful vector. They took the cosine similarity between the embedding vector of doctor and the embedding vector of male and found it was closer than the distance between the embedding of doctor and the embedding of female. Other work found that if you gave GPT-2 the wrong prompt, it would reveal explicit and harmful stereotypes. Even if you had a perfectly unprejudiced dataset, it would be very expensive to retrain a language model from scratch, such as GPT-2 or GPT-3. It would cost on the order of millions of dollars. It would take considerable time. And not only that, but the energy it takes to train a large language model from scratch emits hundreds of tons of CO2 into the environment. All in all, we want a cheaper way to modify our existing language models to do better and mitigate these stereotypes. Finally, even if you do fine-tune a large language model, it might be prone to catastrophic forgetting. This is when an AI model unlearns information when it encounters and trains on new information. And recent work, such as Liu et al., show that you can take a GPT-2 language model pre-trained on English text and then fine-tune it to do various other tasks in various other modalities, such as numerical computation, vision, which is image classification, and then biology, such as protein folding. And this is where our big question comes from. If it is so easy to take a GPT-2 language model pre-trained on English text to fine-tune it on completely different tasks and modalities, then can we mitigate prejudice in these large language models through similar means? Here's an overview of our work. First, we curate a fine-tuning dataset that is free from prejudice according to our definition. Next, we take the publicly available GPT-2 language model and make certain modifications to it. Next, we fine-tune these modified GPT-2 models. Finally, we apply them to the stereoset benchmark, which provides a way for us to quantitatively inspect how well our methods mitigate prejudice. Let me dive into the details of our fine-tuning dataset, which consists of two pre-existing works. The first is the window bias dataset, and the second is the Crow-S pairs dataset. The window bias dataset consists of descriptions of professions and genders such that professions are described with an equal distribution of masculine and feminine pronouns. For example, if there is a sentence that describes a physician as a he, there will be a corresponding sentence that describes a physician as a she, with all else being the same. The Crow-S pairs datasets are very similar to the window bias, but they target other stereotypes beyond just genders and professions. For example, there will be one sentence that describes a traditional stereotype, and then the second sentence is a modification of the first, but it describes either another demographic or another attribute. For example, there could be a female astrophysicist, and then there is a corresponding sentence that is very similar to the first, but it could describe a male astrophysicist. Next, we took the publicly available GPT-2 language model and made one or more of the following modifications. On the left, you see a diagram of the original GPT-2 transformer architecture for reference. By default, all of the layers were frozen so that they wouldn't be changed during the fine-tuning process. Next, we unfroze one or more of the following layers. For example, we could unfreeze the layer norm parameters. We could unfreeze the word embeddings, or we could unfreeze the word positioning embeddings. Now again, we could do one or more of these combinations. The second class of modifications that we did was add a linear input and output layer. There was an input linear transformation, which was applied before the first attention layer. And then finally, there was a output linear layer, which was applied right before the softmax output. And note that these were initialized as an identity matrix. After fine-tuning our modified GPT-2 models on the curated dataset, we can then apply them to the stereoset benchmark, which allows us to measure how effectively we mitigated bias in these language models. Let me break down the stereoset benchmark. It consists of various context association tests, also called CATs for short, which are essentially multiple choice questions, with the prompt being a sentence with one word omitted. The language model has to choose one of three responses that it thinks best fits the sentence. The first option is always a stereotyped response, which represents traditional stereotypes. The second option is an anti-stereotyped word, which is the complete opposite of the first. And then finally, the third option just doesn't make any sense. Thinking about an ideal language model, it should always pick either the stereotyped answer or the anti-stereotyped answer compared to the nonsensical answer. This is captured in the language modeling score that Stereoset calculates. This is one of the three metrics that Stereoset outputs. An ideal language model will have a language modeling score of 100. Next is the stereotype score. This represents the percentage of times that the language model chooses the stereotyped answer over the anti-stereotyped answer. Thinking about a language model that is both accurate and fair, it should choose the stereotyped answer and anti-stereotyped answer with equal probability. Therefore, an ideal stereotype score is 50. And then finally, Stereoset calculates an idealized CAT score, or ICAT, which is a formula involving both the language modeling score and the stereotype score. Now, if you look at this formula, you can see it has some very nice properties. For example, the ICAT score will be 100 if the language modeling score is 100 and the stereotype score is 50. If the language modeling score is 0, the ICAT score is also 0. If the stereotype score is either 100 or 50, representing the language model always picking either the stereotyped answer or the anti-stereotyped answer, then the ICAT score will also be 0. Let's dig into some experimental results. On this table, we have 6 different models, each applied to the Stereoset intrasentence benchmark. The first model is an unmodified GPT-2 model with no fine-tuning whatsoever. This serves as a baseline. The LN model only fine-tuned its layer normalization parameters. The LN plus WPE model only fine-tuned its layer normalization and word position embeddings. The next one has all of the previous modifications with the addition of fine-tuning its word embedding parameters as well. The next model has all of the previous modifications with the addition of a linear input and output transformation as previously described. And then finally, for comparison, we have one GPT-2 model with all of its parameters unfrozen during the fine-tuning process. I want to highlight a few notable results in this table. First of all, the LN plus WPE model, which again only fine-tuned its layer normalization parameters and word positional embeddings, observed the best results on the Stereoset benchmark overall. That model and the LN model observed particularly good results on the gender and profession categories of Stereoset. We believe this is in part because a third of the dataset comes from winnow bias, which focuses on gendered and professional stereotypes. And let me emphasize how many tunable parameters there are in each of these models. You can see the same models from the previous table, and the LN and the LN plus WPE models both observed the best results on the Stereoset benchmark, but they only fine-tuned less than 1% of their total parameters. You can also see that As the number of tunable parameters decreases, so does the training time per epoch. Let me emphasize again, the best performing model overall is the LN plus WPE model, which increased its ICAT score by 3.68% by fine-tuning less than 1% of the model's total parameters. This suggests that a lot of the stereotypical bias that stereoset measures is actually consolidated in these parts of the model. Given our findings, there remain a few open questions. First, how do we reduce prejudice in other demographics beyond the 4 types tested in stereoset? That being gender, race, profession, religion. Second, how much training data is required to effectively mitigate bias in these language models? In our work, we used 4,600 sentences, and that remains static over all experiments. Next, what types of training data or fine-tuning tasks work best? In our work, we used a cross-entropy loss on next word prediction. And finally, is there any prejudice embedded in the model beyond what is tested by stereoset? In conclusion, by fine-tuning less than 1% of parameters in a GPT-2 language model, we're able to improve stereoset scores by up to 3.68%. And stereoset serves as a proxy for stereotypical bias in language models. Our best performing model overall only fine-tuned its layer normalization and word positioning embeddings. This method avoids expensive retraining and catastrophic forgetting. Thank you.